Today, we're diving into a fascinating new paper that offers a completely fresh way to think about quantum information. It's called Spectral Decomposition of Quantum Distinguishability, and it tackles a huge paradox at the heart of modern physics.
So, let's start with a puzzle that seems to just break physics. How is it possible that when you make electrons lazy, slowing them down until they're barely moving, you can create a perfect, resistance-free superconductor? I mean, everything we learn tells us you need moving electrons for electricity, right? But some of the wildest new materials are showing us the exact opposite.
Take a look at Magic-Angle Graphene. It's this exotic material where you have two sheets of carbon atoms and you twist them just so, at this very precise 1.1 degree angle. And that simple twist slows the electrons down to a crawl. And right at the point where they almost stop moving entirely, that's when these incredible properties like superconductivity just pop into existence.
And it's not just superconductivity. Look at the quantum Hall effect. In that phenomenon, electrical conductance gets quantized. It locks into a perfect value, and the precision is just staggering. We're talking 1 part in 10 billion. A level of stability like that tells you something incredibly robust is going on underneath, something that's totally immune to all the usual chaos you'd expect at the quantum level.
So here's the big contradiction, right? Basic physics says an electron with zero velocity shouldn't be able to transport any charge. No movement, no electricity. Simple. But in these amazing materials, the opposite happens. And that contradiction tells us that our picture of how information works at the quantum scale, well, it must be missing something.
Okay, so how do we solve this? Well, the paper we're looking at today proposes a really groundbreaking idea. It suggests that maybe we've been thinking about quantum information all wrong. It's not one thing. It actually travels along two totally separate channels.
And this is the core idea from the paper. Now, I know the language sounds a little dense, but the concept behind it is actually pretty profound. It's saying that our ability to even tell what a quantum state is, to read its information, comes from two different places. One is all about the local, physical details, and the other is about the system's overall global shape, what we call its topology.
So what do they mean by quantum distinguishability? You can think of it as the clarity of the information in a quantum system. If a system is highly distinguishable, it means its state is really clear and easy to read, and that information stays reliable even as the system changes and evolves. It's all about information fidelity. To really get a grip on these two channels, let's use an analogy. Imagine you need to get somewhere, and you have two ways to go. You can take a bumpy, winding local road, or you can hop on a smooth, direct highway. And this is where it just clicks, right? The metric channel is that bumpy local road. It's filled with fragile details about every little twist and turn in the local geometry. But the topological channel, that's your highway. It's robust, it's stable, and it only cares about the overall journey, not the little bumps along the way. Let's break down that metric channel. This is the channel that's all about kinetic energy, the actual movement of electrons. It carries all the information about the density of energy states, and it's super sensitive to every tiny local change. It's basically the noise channel. Trying to get information from it is like trying to navigate a whole city just by looking at the cracks in the pavement.
But then you've got the topological channel. This is your signal. It's what we call metric invariant, which is a fancy way of saying it completely ignores all that local geometric noise. It encodes these big global properties like winding numbers. And this information is unbelievably robust. It's like knowing you're on Highway 1. A few potholes on the road don't change the fact that you're on Highway 1.
And this is the crucial insight. This is the real magic trick. If you have one channel that's full of noise and another that's crystal clear, what if you could just turn off the noise? Well, it turns out physicists have figured out how to do exactly that, and it's an absolute game changer.
So how do they do it? They create what's called a flat band system. In materials like Magic-Angle Graphene, they engineer the quantum state so that the kinetic energy of the electrons drops to almost zero. And since kinetic energy is what drives that noisy metric channel, well, creating a flat band is literally like hitting a mute button on all that noise.
So here's the whole process, what the paper calls dimensional decoupling, and it's really the aha moment. You start with a normal system where both channels are active. You've got the noisy one and the clear one. But then you engineer a flat band, say by twisting your graphene. That vanishing kinetic energy effectively mutes the noisy metrics channel. And what are you left with? Just the pure, ultra-stable signal from the topological channel. And this quote from the paper just nails it. By silencing all that geometric noise from the metric channel, the only information left to read is the system's fundamental, unshakable topology. The signal just emerges crystal clear from the noise.
Okay, so that's the theory. It's a beautiful idea, right? But how does this new two-channel framework actually help us solve those bizarre puzzles we started with?
This framework just cleans everything up so elegantly. For Magic-Angle Graphene, the fact that the electrons stop moving isn't a bug. It's the entire feature. It's what mutes the metric channel and allows these incredibly stable topological properties, like superconductivity, to completely take over. And for the quantum Hall effect, the reason it's so unbelievably precise is because we're essentially reading a signal from a perfectly isolated channel, completely shielded from all that metric noise.
So what's the big takeaway here? Why does this really matter? Because it's not just a cool theory. It's a design principle. It's a recipe for how to actually engineer quantum systems to be robust. By learning how to turn down the noise, we can literally access this hidden, ultra-stable reality that was there all along.
And the future for this is, well, it's huge. This could be the key to designing fault-tolerant quantum computers that are naturally protected from errors. It gives us a whole new toolkit for discovering materials with unique properties we can turn on and off. And even more fundamentally, it just reframes how we think about the relationship between information and noise in the universe itself.
Which leaves us with this incredible kind of mind-bending question. If our entire perception of a system's properties depends on which information channel we're listening to, and now we're learning how to selectively mute those channels, what other features of reality are just waiting for us to control them? What other hidden properties of the universe are out there, waiting for us to finally find the right way to listen?